Welcome to week 4 of 6 of our Introduction to Machine Learning series. This series is focused on learning the math behind supervised machine learning models and get a better understanding on supervised machine learning. This session, we're going to be focusing on linear regression and in the process, explore loss functions, gradient descent, and implement with scikit-learn in Python. This is our first introduction to regression. This session is going to be run by myself, Sumana Ravikrishnan. I'm a data scientist at ServiceNow. And we also have Chinmayi Hota, software engineer at HCL. I will be focusing on the concepts and the theory behind the machine learning model, and Chinmayi will work on implementing it in the second half of the session. So before we start, I want to give a big shout out to all of the volunteers who've put in a lot of effort in this webinar, like putting the content together and presenting and all of that fun stuff. We wouldn't be able to run this without them, and huge shout out to them. Thank you so much for your help, everyone. And also, we wouldn't be here without our sponsors. We thank Home Depot for sponsoring us to be able to put out all of these events in such a needed time. Thank you, Home Depot. And I also wanted to remind you about a remote developer conference that Women Who Code is conducting. It started yesterday. It goes over 3 weeks. It's for 3 Fridays starting yesterday. So we have 2 more sessions coming up, which is the coming up Friday and the Friday after that, which is June 12th and June 19th. This conference is completely free, and you get to talk about anything related to code, community, and career. So highly encourage you to check it out and see if there are events you would like to participate in. And before we start, some housekeeping. Any links that are mentioned during the webinar will be shared in the chat. So if you see any link being mentioned, keep an eye on the chat. One of our panelists should be replying there. If you have any questions during the webinar, please use our Q&A portion, which is there in Zoom, to post any questions you have. Before posting a question, check if anyone else has asked something similar, and if they are, do upvote it. And if you do like some questions that are there and want them to be answered too, please do upvote it so that we can answer them. So the Q&A will be answered during the webinar by our panelists, and all of them will be answered in text format. And at the end of every section, in the theory part at least, if there are any remaining questions which hasn't been addressed, I will pick them up and answer them live. Additionally, if you have any issues like setup, or you're not able to hear what I'm saying, anything at all, please use the chat to chat with the panelists directly and let us know about any issues you're facing in the process. Awesome. So let's get started. So this is our 4th session of the 6-week session. This is going to be our first introduction to regression. We're going to learn about what regression is by starting off with linear regression, the simplest one. And then linear regression internally uses loss functions, which leads to gradient descent. So we're going to be touching upon these two. So the 2-hour session is split into 2. The first hour, we're going to be focusing on concepts and problems. And this will be run by me. And the second half is going to be a Google Colab project. We will provide the code and the data, and Chinmayi will go over how the code is run, answer your questions on any questions you have on the data or any of the code that she's written. So a quick reminder of what all we have covered till now. We got introduced to supervised learning in week 1. Then we saw our first classification algorithm using conditional probability using Bayes' theorem. Then we went on to see how else probability can be used using statistics like information gain, entropy, to build something called a decision tree. And we also saw something called ensemble learning, which mixes models together, and how random forest is an ensemble of decision tree. This week, we're going to be checking out linear regression, which is our first regression function that we're seeing, and see loss function and gradient descent in the process. So a quick recap of what regression is. Regression is when the target responses are continuous or numerical in nature. Some examples of regression are stock prices, being able to predict the stock prices in the future, being able to predict the costs of aeroplane tickets in the future, being able to predict what a person's credit score would be based on their history, being able to predict the supply chain management, and making sports projections during big events and so on. So these are some examples, but there are a lot more examples of regression too. So let's start off with linear regression. So linear regression is used to find a linear relationship between a target response and one or more features. So quick recap of what feature and target response is. Features are our X values, which would be the input columns. Target response is Y, which would be our predict column. And both are continuous in nature, which means both Xi and Y have to be numerical in nature and have a numerical value associated with it. It doesn't just have to be numerical, it has to be continuous, means that they have an inherent ordering to it. So there are a variety of applications for linear regression, like historical stock prices. So based on the historical stock prices, the future stock price is going to increase in a kind of linear fashion. A team's future performance can be predicted based on their past performance in a linear fashion. The power consumption of a function or a process can be predicted using how much what process it is and how much memory it uses. So predicting the future based on past using continuous values, which have a linear relationship between them, is linear regression. So let's take a look at a simple example. Here we have a graph which has on the x-axis the SAT math scores, and on the y-axis the college GPA scores. And we want to see if there is an existing relationship between a person's math score which they achieved in school or right when they were getting out of school versus the GPA scores when they're done in college, to see if they're equatable. I want to say I have this data set. I want to see, is there a relationship between these two? If I know someone got this much score in SAT, in their SAT math, will I be able to predict what the college GPA score would be? So in this case, say I have a bunch of data points which I have collected from a given school. Um, and the GPA scores are collected when they graduate. And I've plotted plotted a graph with all these values. So as far as linear regression goes, the main goal is to basically plot a linear line or a straight line, which can cover as many data points as possible in this. So what linear regression's goal is to predict the formula of this line so that it covers as many data points as possible and minimizes the loss. We'll take a look at what loss means in just a quick second. So as I said, we have a lot of data points and our goal is to find a regression line, a line that best fits your data. It has to cover as many data points as possible and be as close to as many data points as possible to reduce the loss. So in this case, we have just one input feature xi and one target response y, which is plotted in a 2D space to predict a line, a regression, which is a combination of the x and y values. So the red line is the one we predict, given the blue dots, which is our data points. So let's visit a formula that we've learned in school in linear algebra. So y is equal to mx plus b. I'm pretty sure this formula must be etched in everyone's minds, but it was etched in mine too until I revisited it when I was learning linear regression myself, and then got a better understanding on how linear algebra is linked with machine learning, how tight the relationship there is. So coming back to the formula, y is equal to mx plus b. This is a formula of any straight line that can be plotted in a 2D space, where y is the y-axis, x is the x-axis. So we have the x-axis and the y-axis. for any given line that's there, this line can have a slope of m. A slope is basically, in the most simple terms, the angle at which a line is. So slope is calculated by using the differential of x divided by the differential of y, just showing us what angle the line has to be in. So m is the slope of the line. So if you know what angle the line is at, if you know where it intercepts the y-axis, where x is equal to 0, which will give the value b, you can formulate this as y is equal to mx plus b, where y is our predictor variable, aka target response. M is the slope of the line that we're predicting, the regression line. X is the dependent variable, which is our input feature xi. And b is the y-intercept, the location, the value of y when x is equal to 0, where it intersects the y-axis. So let's reformulate this to fit our question. So we saw a graph which had xi versus y. So let's just plug in those values into this and redefine what m and c are. So here y is remaining the same because y is our target response. X is remaining the same because it's our feature xi. We're renaming the slope of the line for a given feature x as bi. So the slope of xi is going to be bi. And the intercept value is going to be renamed to b naught. So in the case where we have one feature, say this graph, and I have x1 here, this would be y is equal to b1 x1 plus b naught. So this is our final formula that we're going to be using when we have one input feature and one target response. So now we know that for one feature linear regression, this is the formula. So you solve for y when you have samples of xi and y. Solving for y basically means you're solving for a function x, f of x, which is equal to y. You're solving for what f of x actually is. So that's what solving for y means. So in this case, this was the formula we saw in the previous slide. And then plugging in the formula for slope and the formula for intercept, we're getting bi is equal to the differential of y with respect to the differential of x. So you get the slope of xi based on that. B naught is basically, we're rearranging this to get the corresponding value of B naught. So just moving this entire thing over to this side, you can consider C to be xi in this case. So our goal is to predict, get to a value of bi if other values are known. And then if x and y values are known in our input features. And then using bi, get to the value of b naught. And that would give you f of x. So this is a very simple example where we have only one input feature. But then that is not what you see in real life, right? It's usually more than one feature. Even the simplest example we saw of playing golf, it took 4 input features such as humidity, windy, temperature, and outlook, and predicted whether you would play golf or not. So what happens when we have more than one input feature? So that's when you start plugging in the values of x1, x2, so on, wherever xi was present. So each feature would produce b1 x1 or bi xi basically. And we still have the same y-intercept. But then if you think about this, this would be plotted in an n-dimensional space. Each of these, n+1 dimensional space to be precise. So each of the x values would be an axis, plus y would also be an axis. So this would basically increase the length of this formula by adding more terms. And each term is a value for a given feature. So putting them both together, linear regression has 2 types. There's the simple linear regression and the multiple linear regression. So as far as simple goes, there's only one input feature and b1, x1 is the only variable there. As far as multiple linear regression goes, there are n input features, and this would be plotted in a n+1 dimension space. Okay, I'm just going to quickly answer some questions before moving on to the next section. So the first question is, I'm a little confused about the part where we're calling differential, the x bar, x and x bar. So I'm just going to move back to that slide. So over here, if you see, this is the formula of slope. So if you Google up the formula of slope, it's possible to calculate the slope of x if you have data points for the values of x and y. Basically, if you have data points mapping to this, if I know, say, 20 data points or x number of data points, that is enough for me to find the relationship between the two, which is the slope. So using that, this is the formula that is used, the simple formula that is used to calculate the slope. Here, x bar is the mean value of x, y bar is the mean value of target response, x bar again is the mean value of x. So you're basically getting the difference of your current x value to the mean, how deviated from the mean your current value is, how deviated from the mean your current predicted value is, which is target response, and calculating the slope based on that. So this is just plugging and playing those formula values. So could you explain the formula for BI again, where you sum up something from with the differences of the means? So Tanya, I hope this answers your question. It's the same thing. So this is just the formula for slope. If you guys can Google the formula of slope, you'll get a better understanding on how, if I have a table with x and y values, say x has 1, y has 10, x has 2, y has 20, x has 3, y has 30. So first thing I would do is calculate the mean of my x column, calculate the mean of my y column, and then plug and play for each row in this. So for each row, which my first row where the x value was 1, I will do 1 minus 2 into, I think the mean of 10, 20, 30 would be 20. So 10 minus 20 divided by 1 minus 2. Next one would be 2 minus 2, 20 minus 20, 20 minus 20, and so on. So you would get multiple values, which you would summation up to get your corresponding slope. Okay, and perfect. Okay, and okay, before we go, there's a last question. So someone's asking that they are a teacher and they would like to switch their career to a data scientist. There are so many different schools and online courses. I'm not sure where to start. So we have suggested a couple of good online resources for these tools. My top recommendation is Coursera. They have really good machine learning specializations, and Andrew Ng is my all-time favorite teacher. I've added a bunch of his explanation videos at the end of this presentation too. So you can take a look at it and see, get a better understanding on these concepts. But I would suggest to start exploring by yourself to see if it is something you like before jumping into paying for school and stuff. And my last question here, do the features have to be continuous or only the response variable? So for linear regression, both have to be continuous. Okay, so moving on. So now we saw that our goal is to solve for y. So say that you have this given graph that you see here with n number of data points, which are marked in black. There are multiple different possibilities for y that I can solve, or multiple lines that I can generate, which could be a good fit for this data. But our goal is to see what is the best fit. Even though you have so many possible lines based on what slope you're calculating, each could possibly have their own repercussions, to say. So in classification, we saw that we were calculating the accuracy based on how many it got right versus how many it got wrong, and so on. We need to see how to evaluate it when it comes to regression too. So in this case, say I have 20 data points as shown in this. I'm able to generate 3 f of x, which is I solved for 3 y's, and all 3 seem to be good fits. How do I evaluate between them to know which one's the best? So for this, we use something called a loss function. So loss function is basically a measure of how good your prediction model y is able to predict the expected outcome. So it does this by measuring the deviation of prediction model from the expected outcome. So our goal, we can change it to convert this into an optimization problem where you can define a loss function and then say that pick the line with the minimal loss. So try to pick the line with the minimal loss. So going back to the image from the previous slide, I can generate n number of lines I want, but each of these lines, I can calculate a loss for it. And this loss value can be compared against each other to see which one is the best fit. So our next question would be, how do I calculate the deviation? We saw that we want to measure the deviation, right? So we do this using a concept called residuals. So in this case, in the graph you see, the blue dots are the actual data points that you have observed historically. The blue line is what your prediction model is predicting to be the best fit. So in this case, a residual of a data point is how far away from the prediction the data point is. So if I were to input this data value x into this model would actually predict y is equal to -60, while the actual value of y is closer to -38 maybe. So our goal is to measure the difference between the two to get an overall estimate of how badly or how well my regression model is fitting all of my data points. So our goal for a given regression line is to see how much each of the data points in the data set deviates from the regression line, add them up, and use a metric to evaluate them. So our goal is to get a metric. So loss function, there are multiple possible loss functions you could possibly use. I'm just going to go over three pretty popular ones. There are other ones too, which are lesser popular, but might fit the problem that you're doing using better. So loss functions are completely dependent on the problem, the use case, the data set, whether you want to minimize the loss or you want to maximize the loss. Like a lot of factors are involved. And based on that, you get to pick which loss function goes. So I'm going to go over three of them, and I highly encourage you to check out more after this session. So the first one we're going to see is called mean absolute error. So mean absolute error measures the average magnitude of errors in the set of predictions without any consideration of the direction. So what does without any consideration of direction mean? Because we're taking the absolute value, as you see here, you don't know. I'm just going to go back to the previous one. You don't know whether your data point lies above or below your line. So you just know that this point is, has a 20 loss. Even this point would have a 20 loss. There's no way of differentiating which direction, whether it's a +20 or a -20, basically. So that is a method that's used, a loss function, which is mean absolute error. And this is basically done by taking the average absolute loss that's done in the model. So coming back to the diagram, I would just calculate for every data point, get the loss for that data point, the absolute loss for that data point, add them all up and divide by the number of data points. That's exactly what this is doing. So y cap, as a reminder, is the predicted value. Y is the actual value. It doesn't matter what order this is in because we are taking absolute in the end. For every data point, you see how much it deviates, how much the actual value deviates from the predicted value. Add them all up and get an average of it. So the average magnitude of errors in a set of predictions. So from the looks of this value cannot be negative. So this value ranges from 0 to infinity. And minimizing the loss is basically our goal. So the lowest value is preferred. So this does not quantify direction of error, as we saw. And each individual data point is weighted equally when it comes to this. So the next one we're going to see is mean squared error. It's the exact same as before, but instead of the absolute value of the difference, we're going to go with squared value of the difference. So why are we doing absolute or absoluting it or applying a square value to it. The reason for this is, since we're doing a summation, we need to make sure that the internal value is also positive so that the summation does what it's expected to instead of nullifying the result. So that's why we need to make sure that the internal value is positive. So in this case, we're doing a squared instead, where we're squaring the difference between the actual and predicted value for every data point and averaging it over your data set. So this value too will always be positive. So it ranges from 0 to infinity, and the lowest value is preferred. It does not quantify the direction of error. One thing to note here is, since we're squaring the error associated with each data point, the differences are not weighted equally. So a data point which has a deviation of say 10 would have a total impact of 100, while a data point which has a deviation of 2 would have a total impact of just 4. So it completely depends on how much deviation is there. But as you can see, as the deviation is increased, the weighting for that data point is higher. So therefore, this makes it highly sensitive to outliers and variance. And because like the outlier would have say 100 distance from the prediction, this would make it like a very high error model just because that one outlier was included in. So mean squared error is the second one. So to overcome the challenge of the squared error that we're seeing, where the outliers are impacted by it, we're going to just apply a root on our entire thing. So RMSE is basically a root mean square error, and RMSE is a short form that's used. So RMSE is a quadratic scoring rule that measures the average magnitude of error, which has been square rooted. So it's the exact same formula as before. Find the difference between the actual and predicted and square the error and average it out over your data set. And we're nullifying the square that we're doing inside the summation with a root value on the outside. So even with this, it's always going to be positive. So the value ranges from 0 to infinity, and the lowest value is preferred. And same as before, this does not quantify direction, and it's not good if direction is important to your problem. And differences are not weighted equally. It is giving a higher weightage to the outliers or the data points that are outside. But this isn't as sensitive as MSE is. The sensitivity is reduced a little bit because we're applying root to our result, but it is sensitive, more sensitive than mean absolute error to outliers and variance. Okay, quickly answering some questions I see. So both the questions are asking about which loss function is the best. So that completely depends on the data set you're working on. Say the data set you're working on, the direction of the error is important. In that case, all these three will not fit because it does not quantify the direction of error. So it completely depends on the data set you're working with, whether you want to give higher weightage to outliers, whether you want to give lower weightage to the outliers, and how you're formulating the question. So this is also very dependent on the data set. Actually, most machine learning concepts are that way, where it is a concept by itself and it does not fit everything, which is it's completely subjective to the data you provide, the problem you formulate on your data, and what data exists in these columns that you're providing. So there's no one good answer to that, to answer your question. So we've seen 3 loss functions, and we're going to move on to see how we're calculating the residuals and loss. So our goal would be to minimize our loss. The regression line, which basically fits most of our data points, would be the one with the minimal loss. So, so if we see this on the left, we already saw this diagram where we had like 3 different possible fits of linear regression for our data set. On the right, we see how for each given line, you calculate the residuals and inherently calculate the loss of that line. So let's consider an example. So consider an example data set of 100 people in the graph on the top left. So we have their heights on the x-axis, their weights on the y-axis, and plotting them, I see like a linear relationship, kind of linear relationship between them. As their height is lower, the weight is lower. As their height increases, the weight also increases. So we know our formula of y is equal to b1 x1 plus b0. In this case, I'm defining x to be my height and y to be my weight. So knowing that, I know the formula for B1. I just need the values of X, each data point of X, which is there in this graph, each corresponding data point of Y, which is also there in this graph, the mean value of X and the mean value of Y. That is also present in this graph. So I think I have everything I need to calculate the value of B1. So by doing that, I calculate the value to be this given line, which I'm plotting right here. This angle of the line, basically, a line with this slope. So now that I've estimated the slope, this slope estimation is also done with least squares to see which slope gives the least error. So it tries it out for multiple different slopes and narrows down on the best slope using least squares. So now that we have this value already plugged in, it'll be easy for us to rearrange this to estimate this value using gradient descent. So what we need to, so now that we found the best value for B1 using least squares, we need to find the best value for B0 given B1 exists. So going to the next one, what does this actually mean? What does B0 could be anything mean? So now that I predicted that this slope with this line, which was estimated using least squares, is the best line, I can place this anywhere on the y-axis, meaning this line can start anywhere on the y-axis over here, meaning it can intercept anywhere over here. So that's what B0 actually means, which is you're trying to vary the value of your y-intercept. Y-intercept here is when your x value of y when x is equal to 0. You're basically varying this to see which one gives the best fit. So in this case, what we're going to do is we're going to calculate the cost. We're going to see what cost actually means. We're going to calculate the cost or the loss associated with this line, the loss associated with the next line. So we can do that for each of these lines pretty much. And one thing to note is that if you do this, one constant kind of relationship that you see between the intercept and the cost or loss associated is basically that the cost is minimal for an intercept value. And as the intercept changes on either side, the cost or loss dramatically increases. So this is a general kind of structure you see in any intercept versus cost or intercept versus loss graphs, where the cost, you have higher cost for the highest cost for intercepts that are furthest away from the best intercept, and the lowest cost for the intercept values that are closer to the best intercept. So technically what we have to do is we already have this. I'm going to try out a bunch of different values for B0, and a bunch in this case could be every possible value that exists from, say, outside this, so that I can fit this value also, like maybe 120 till I want to fit this value also, say till 180. So 120 to 180, I need to test all possible values. And if it was, if it were the case, I could also test within the steps of 120 to 180. I can go starting from 120.00, 120.01, 120.02, and imagine the number of cases I will get till 180. And this is the case where I'm just considering the precision level being 2. There are instances where you need the precision to be super high. And in that case, this would add up to be too many possible calculations that you can do. If I need to plot this graph, I need to calculate so many different values to arrive at what is the best intercept. So for this, we're going to, so this is the process of gradient descent. And gradient descent can add up to having too many calculations for you to do. That might be a problem. So for this, we use something called an optimization function. So as we saw, we have the cost intercept graph. I want to quickly remind you that cost here actually means loss. They're both the same thing. And these terms will mostly be used like interchangeably in most of the documents you see online too. So cost and loss are the same. So you want your loss to be minimal and your cost to be minimal too. So coming back to this graph, we saw the cost and intercept graph looks similar to this. And we know that these are the higher cost values, these are the lower cost values down here. And if we were to test every possible value along this line, these calculations can tend to be way too expensive than we need it to be. So that's why we need an optimization function, which basically reduces the number of calculations we have to do when it comes to this. So on the left here, we see the graph that we just saw. And on the left, I want to remind, this is the case where the intercept and the cost have only been plotted. I want to show you how it would look correspondingly if you were to plot it in a 3D space where you have x value on the x-axis, y value on the y-axis, and the cost/loss associated on the z-axis here. So this is the kind of cost intercept, cost curve that you kind of get. And these are the possibilities of all possible values of x and y, which can give you this kind of cost possible. So this diagram on the left can be directly mapped to the first diagram here on the right. This is an ideal scenario where it's like completely smooth and helps you reach your minimal cost the best way possible. So coming back to the text here. So in the case of loss function, an optimization problem consists of minimizing the loss by systematically choosing input values from within an allowed set and computing the loss for that function. What does that mean? So for every combination of x comma y, I'm going to calculate the corresponding loss for that linear regression function that I have created. So if I do that, I will plot points along this entire thing. And my goal is to pick something that has the minimal value along the z-axis. And here on the right, you have something similar to, but then this is a non-ideal scenario where your cost curve can be of any form too. This is an ideal form, but it can exist in this form again, this form too. So the main thing to note here is our goal is to get to the bottom of this. So the optimization function is basically if I start rolling a ball from the top with the maximum cost, I want the ball to roll down to the minimum cost, and whatever value it reaches, that would be the best B naught value, the corresponding best B naught value I can set for my gradient descent. So moving on to the next one. Actually, before that, so one thing we need to note here is, from the example I explained, we want to start rolling the ball from the top till it reaches the bottom. So let us define what top and bottom actually mean. So the terminology I want to introduce to you at this point is extrema. So extrema is basically the largest or smallest value that can be produced by a function f. I want to quickly move back. This is our function f. The visual of this is basically our function f. So within extrema, there are two types of extrema, which are local and global. So local can be within a given range, and global can be on the entire data set. So moving back to our example here, if I were to look at only this locality, this point right here in the bottom most would be my local minima, but it is not my global minima. Okay, and extrema, there are two types of extrema based on the value, because it can be either largest or smallest. So maxima is the maximum value that can be there, and minima is the minimum value that can be there. So one thing I want you to note is extrema is a single, actually extrema is the plural of extremum. similar to how maxima is the plural of maximum and minima is the plural of minimum. So minimum is a data point. Minima is for your entire data set. That is the minimum value. So from this graph right here, say I'm defining 0.6 to 1.2 to be my local range, 0 to 1.2 to be my global range for the entire data. If I were to take between 0.6 and 1.2, this is where my data reaches its maximum, which would be a local maxima. And then this is where my data is reaching the minimum, which would be my local minima. And if we were to consider the entire data set, these two aren't overall minima and maxima. So we're going to reset it as this is the global maximum and this is the global minimum. So basically for any curved line, there can be 4 possible values, which are local and global maxima and local and global minima. So before I head on into gradient descent, I'm just going to answer a question I see here, which is, can you explain cost again? So yes, I can. And the main thing to note here is cost and loss are the same thing. So I'm just going to explain loss, and that should give you a good idea on what cost is. So loss is basically how much deviation or how much loss your given prediction is going to incur. So in this case, this one has this much loss. So why is it called cost also? So cost is something that's used in problems and stuff, where some of the problems could have a cost associated with it. Say if my data point is n points away from my line, it's going to cost me $10. If it's 20 points away, $20, and so on. So using this loss, you can calculate a tangible value of how much it would cost you or how much money you would lose with this. So not all problems have money involved. So that's why loss and cost are interchangeably used based on what problem it is, but they both internally mean the same thing. Okay, so I'm going to be moving into gradient descent. This is a very interesting topic, which I'm excited to share with you all. So gradient descent is something that was proposed in 1847, if you can believe it. It's been around for the longest time, and it was proposed by Cauchy. So gradient descent is basically an iterative optimization algorithm for finding a local minimum of a differentiable function. Our differentiable function in this case is the graph that we're drawing, which looks like the inverted mountain. And our goal is to find a local minimum in that. Continuously, iteratively find the local minimum until the local and global minimum coincide. So gradient descent is also known as steepest descent. We'll be looking at an analogy to understand this better in the next slide. But please bear with me, this part might not make sense. The analogy would make sense. So looking at the third point here, so gradient descent goes off of this. So if you have a function f of x and it is differentiable in the neighborhood of point A, then f of x decreases fastest if one goes from A in the direction of negative gradient of f. So keep this in mind while we check out the analogy and revisit this. So ignore the thing on the left. We'll revisit it after we check out the analogy. So say you're someone who's stuck in the mountains and your goal is to get to the base of the mountain. The fog is super heavy and you can't see anything beyond, say, 10 feet. Your local range which you can view at is only 10 feet, but you need to get to the base of the mountain. You start off at the top, like say at sunrise, and your goal is to get down before sunset. So since the path down is not visible, we have to use gradient descent along with local information to find this. So local information here is the 10-foot radius around you, which is visible and which you can see. So in this case, what you want to do is in the 10-foot radius that you're standing in, you need to find the steepness of the hill at the current position you are standing in and find out which direction is the most steepest descent, where you can go down the most in the 10 feet. So once you find the angle at which you can do this, you would go along the path. So you can keep doing this iteratively. For every 10 feet, go down the steepest path. For every 10 feet, go down the steepest path. So you can iteratively do this till you reach the base of the mountain. So one more assumption you need to make is that steepness of the hill is not immediately obvious. Like you need to measure it with, say, a given instrument. It is a sophisticated instrument, and this instrument is not very easy to use. It takes time to use it for each and every step. So we can't afford to do this for every step, right? So in this 10 feet radius, if I find a steep path and go down it, I can't keep measuring every 10 steps that I take to see what the steepness would be. Say it has a cost associated with it. Say it takes me 20 minutes to measure the steepness of it. If I keep doing this every 10 steps, will I be able to reach the bottom by sunset? Might be a little tough. So we need to minimize the usage of this. We don't have to keep measuring every 10 feet. We need to measure more smartly. And that's where gradient descent comes in. So let's look at the mapping over here. So the person here is the algorithm itself. So the algorithm should find the steepest descent and go down it. So the mountain's base is the global minima, and where you're standing is the maximum cost or the highest cost you're at, and which is the global maxima. And you need to reach the global minima from there. So your path down from global maxima to global minima is basically the sequence of parameters the algorithm will explore. The steepness of the mountain is basically the slope of the error surface. The instrument that we're using here is basically differentiation. And the time taken is also called as learning rate. So moving back to our definition. So for a multivariable function f of x, which is the person, is defined in a differentiable neighborhood of point A. A is where they're starting off. Differentiable neighborhood is the 10 feet radius. F of x decreases the fastest if one goes from A in the direction of negative gradient of f. Direction of negative gradient of f is basically the steepest path. And f of x decreases fastest if one goes down the steepest path, basically. So I hope this analogy helped. And I found this analogy on Wikipedia, and I was really, really impressed by it. And I thought I should share this with you all. So going into the types of gradient descent that we see, there are totally 3 types of gradient descent. The first one is batch. So actually, I want to just quickly revisit our definition of this. So it's an iterative optimization algorithm for finding the local minimum of a differentiable function. And so at every point, we need to calculate what the next steepest point would be that we can reach, and do the same for the entirety of our plot. So since it's an iterative method for optimizing an objective function, so for each iteration, that is for each data point, it's going to use the whole data set in each iteration. So this would be a good comparison for this would be when the visibility is very high, and you can see wherever you want when you're at the top of the mountain. You're going to measure your entire mountain before you pick your first step. Then you measure your entire mountain again before you pick your next step. So iteratively, you're taking into account all the data points in your mountain pretty much. So the whole data set is used in each iteration. So some features of gradient descent are, some features of batch gradient descent are, it's brute force because it's taking everything into account in every step. And because it is taking everything into account, this is a stable learning path. There are not too many fluctuations and so on. You get to see a diagram to see this explained a little better in the coming up slides. But basically, it produces a more stable path. And if the training data set is too big, for every iteration, it needs to take the whole data set into account and do calculations on the entire data set. So this can turn to be computationally, it could turn to be a burden computationally if the training data set is large, which is basically most data sets right now. So the next one we're going to see is stochastic gradient descent. And this is a pretty popular one that's used. So stochastic basically means randomly determined, or having a random probability distribution or pattern that may be analyzed statistically but may not be predicted precisely. So stochastic is basically a random data point from your data set, one data point. So stochastic gradient descent, it basically does an approximation of gradient descent. Instead of doing it on the whole data set, it does it on one data point, one randomly picked data point from your data set. So this turns out to be especially valuable in big data when it reduces the computational burden and gets your results faster than what a batch gradient descent would do. So if you see the diagram for this, you know that the higher cost would be towards the top, lower cost will be towards the bottom. So the process, the procedure that it takes into account is basically that if it's higher cost, then I'm going to calculate lesser values in this area. I want to go down my steep path and calculate more values when the cost is lower. So what it does is it calculates lesser value when the cost is higher, and cost is higher and the slope is maximum, and calculates values, calculates more values when the slope is lesser, when the curve is like flattening out a little bit pretty much. So how it does this is using this, where for every step is basically an iteration done. So say it starts from this point. So it calculates the slope of this line and the learning rate, and calculates the next intercept based on these values. So since this has a higher cost, I expect the next intercept to be much lower, as compared to since this has a lower cost, the next intercept will be way closer. So this is how gradient descent is used to narrow down to your minimum value quicker. If it's steep, continue down the path. If it starts flattening, calculate more. So mini batch is basically the third type, which combines the concept of batch and stochastic. So batch, it took our entire data set. Stochastic took a single record. So instead, mini batch takes a subset of rows instead. So at each step, the algorithm computes gradient descent on a subset of training data instead of the full batch set or only one record. So the cost function, because of this, decreases a little more smoothly. It's not as jagged as stochastic. And therefore it turns out to be more stable than stochastic, but it is less stable than batch, but then it converges faster than batch. So this diagram might give a better idea on this. So say this is the hill. They've just been printed as concentric circles in this case, but imagine it in a 3D space. This is more helpful for visualizing each iteration, where each iteration is a circle. So in this case, batch takes the whole data set into account. So as you can see, this path is super stable for it to converge at the best possible value for B naught. Next up, we saw stochastic. And if you see stochastic, since it takes one random data point, since there's a randomization involved in it, it tends to be a little more jagged and more confused, and takes a little longer to converge at the same data point. It takes more steps to converge at the same data point. But since it takes only one data point into consideration, it turns out to take more steps. So this one has more iterations, lesser time to converge. This one has lesser iterations, more time to converge. And then we have our middle ground, which is our mini batch, where it is not as stable as a batch, but shows greater stability than stochastic, and greater stability than stochastic because it considers lesser data points. The number of steps also increase. So the number of steps fall between batch and stochastic, and the time to run would also similarly fall between batch and stochastic. It's a kind of middle ground. So I'm just going to answer some quick questions before moving on to the last section, which is sparse learning. So question is, which gradient descent method do you recommend for beginners to use, or does it depend on the data set? So it does depend on the data set, and it also kind of depends on a lot of other features, because it depends. If your data set has too many outliers, this might not be a good approximation because it might send it out in a different tangent and might take more time for you to come back to the right path. So it completely depends on your data set and also on how much computational power you have and how much memory you have to invest in the model. So best case scenario is using batch, but that is given you have TBs and TBs of processing power in your hands. Okay, so since we have just 5 more minutes, I'm going to let the panelists continue with the Q&A and cover up the last section. So now that we saw how we can approximate a linear regression line, and then given that linear regression line, there are two parameters, bi or b1, b2, b3 till bn, and b not have to be approximated. We approximate the bi values using least squares or basically a loss function. And then we approximate b naught value using gradient descent, which internally uses a loss function too. So we saw that till now. But what if the data set is sparse? So what happens if the plotted data points are really sparse and has a high loss even for the best result? What do we do in that case? So say that I have a 3-dimensional space with x, y, and z values, and say y is the value I want to predict. And these are the data points I have. Like from quick visual inspection, I can't think of a single line that will fit all these data points. So what do we do if that happens? And this is something that happens a lot in modern applications where the number of predictors or the input features can be extremely large. An example for this would be using gene data, where gene data basically has measurements from thousands of genes, given that each row of data can have thousands of columns. So this would be plotted in a 1,000-dimensional space, making our data even more sparse than it is. So as you keep increasing your dimensionality, the sparseness of your data increases, and that is called the curse of dimensionality too. So how do we overcome something like this? So there are a couple of methods we can use. The main ones are feature subsetting, regularization, and dimension reduction. So first one is feature subsetting. So feature subsetting is what exactly you think it means. It is you select a subset of features of relevant predictors or input features from the training data, and then evaluate the least fit of all possible sparse models. So to explain this a little better, so say I have 1,000 columns in my gene data, and I define a property saying I want to use only 100 columns from this to make my model. So in that case, like what it does is it calculates all possible combinations of 10 columns from the 1,000 columns and creates models for each of these, compares the best fit across them, and produces the answer based on that. An example here is if n is the number of features, which is 100, your data has 100 columns, and S is the number of input features you want to model. Say out of the 100 columns, I want to model only 10 columns. This basically produces 10 power 13 possible models. So this is actually 10 power 13, not 1,013 models here. So this inherently makes those many possible models that are to be created. And with modeling comes the computational cost that's needed. And this will increase the number of computations made. Since it's more brute force, it tends to be computationally heavy. So there are possibilities for you to optimize this too. And there are functions which optimizes on the feature subsetting process. Another way you can deal with sparse learning is using regularization. So if there is noise in your training data, then the estimated coefficients won't generalize well to the future data. So if I have outliers in my current data set and my model has been created using the outliers, my future data point, which is not an outlier, will get an outlier-like prediction. So using regularization, this method basically assigns weights for each feature, for each column, and then shrinks the estimates for that feature towards 0. So it assigns weights. Higher weights will be given to columns which are providing more information about the prediction. Lower weight will be given to the other columns. So in this case, in other words, this technique basically discourages learning of a more complex or flexible model so as to avoid the risk of overfitting. In simpler words, this basically means it's going to take my columns of 100 columns, assign weights for these 100 columns, and try to shrink the weights for these 100 columns to 0 as much as possible, so as to use the least number of columns needed to make the prediction. So it's best to do this so as to not overfit your model. If you use all your columns, that creates overfitting, and overfitting is the one that is sensitive to outliers. And that is something we want to avoid. So this fitting or shrinking procedure involves a loss function, which is known as residual sum of squares, or RSS. So RSS is basically defined using this formula. I want to point out to you the formula that we had before. Y is equal to B1 X1 plus B0. So basically this is just that formula put together on one side equal to 0. We're summing up all the errors that you get out of it, squaring it up to produce this RSS, residual sum of squares value. This RSS is used internally iteratively to change up the weights of each feature that's there. So in regularization, we have 3 types of regularization. I'm going to go over to the third one is just basically a combination of these 2. So the first one we're going to see is called Lasso, or L1 regularization. So Lasso is basically least absolute shrinkage and selection operator. So basically it calculates the magnitude of absolute value, absolute error, and the coefficient as a penalty term to the loss function. So the same formula that we saw before is here, where we have B1 X1, B0 is here, and lambda is added to the B0 value. So the penalty is added to the y-intercept value. So in this case, if lambda is equal to 0, the squared error will be very high, leading to underfitting. So Lasso shrinks the less important features and coefficients to 0, thus removing some features altogether. So this is a good way for you to remove features completely. I just see a quick question about a correction in a slide, which I want to address. So the question is, what is the correction? So in slide, I'm not sure which slide this is, but the feature subsetting side for sparse learning, this is actually 10 power 13. It isn't 1013. Okay, so moving back, we saw L1 regularization, which is basically adding a lambda or a weight to the intercept value that we calculate. And this is the absolute value of magnitude. So if the lambda is equal to 0, B1 B0 value is also going to tend to 0, which would increase our squared error to be very high. And if our squared error is high, this leads to underfitting. So Lasso is good for you to shrink the less important features and features coefficients to 0 and removing some features altogether. So the next one up is Ridge, which is the exact same formula as before, but instead of taking the absolute value of the intercept, we're going to take the squared value of the intercept. We saw the same thing with MAE and MSE too, where both can be done, and depending on whether your data set is sensitive to outliers or not, you can pick one of the 2. So it basically adds the squared magnitude. So in this case, how it affects us is, if the lambda is very large, this will add too much weight and this will lead to underfitting, which is what we saw before. From there, you can see that as lambda becomes larger, the variance decreases, which leads to an increase in bias. So we again come back to the problem of the bias variance trade-off. So that is also again comes back to your data set. How much bias are you willing to accept in order to decrease the variance? Our goal is to decrease the variance, but to decrease the variance, you need to accept some bias in your data set. And then the last section here is dimension reduction. So dimensionality reduction is the process of reducing the dimensions of your feature set. So in simple words, I want to take 1,000 columns and compress it down to 10 columns, compress in quotes. So compress is what we're going to see how it's done. So your feature set could be a data set with 100 columns and could be an array of data points that make up a large sphere in 3D space. So dimensionality is reduction is basically when you take something from an ND space and reduce it to a MD space where M is less than N. So in this case, you're taking a sphere from a 3D space and converting to a circle in a 2D space. So this can be done using linear transformations, and there are some other methods too. We're going to be going over the linear transformation methods. I want to just quickly step back about the regularization. So the third type of regularization is called elastic net, which uses a combination of both L1 and L2 regularization. And L1 and L2 regularization is also called penalty, because this lambda is a penalty that's added to your data set. Okay, so coming back to dimension reduction, there are three types of dimension reduction that can be done using linear transformations. There are many more too. We're just going to go over three. So PCA, or principal component analysis, which is a very popular dimensionality reduction process that's used today. It basically rotates and projects your data along the direction of increasing variance, and features the maximum variance as the principal components. So this is popularly used for dimensionality reduction in continuous data. And the next one up is factor analysis. This is a technique that is used to reduce a large number of variables into fewer number of factors. The values of the observed data are expressed as functions, and the number of possible causes in order to find which are most important. The observations are assumed to be caused by a linear transformation of lower dimension latent factors and added Gaussian noise. So this might be a little over the head, but this is a possible way for you to explore if you encounter the issue of sparse learning. The next one up is LDA, which is linear discriminant analysis. So this basically projects your data in a way that class separability is maximized. So one thing to note is this one is for classification specifically. So examples from the same class are put closely together in the projection, and examples from different classes are placed as far apart as possible by the projection. So LDA can be used for classification problems, and PCA and factor analysis can be used for regression problems. So a quick recap of everything that we've looked through now. We saw what linear regression is. We saw single and multiple linear regression and how these formulas are created using linear algebra. We saw what residuals mean to measure how bad or good your fit is. And then these residuals are internally used by loss functions to calculate the loss of a given fit. We went over MAE, MSE, and RMSE, which are mean absolute error, mean squared error, and root mean squared error. Then using that, we finalized what our BI value would be. We needed to finalize our B naught value. For that, we're using something called gradient descent. We saw what gradient descent does, which is internally just an optimization function. We saw its three types, and which were batch, stochastic, and mini batch. Stochastic is the one we'll be implementing today. We also saw the pitfalls of regression when the dimensions are increased, which leads to sparse learning. We saw how to overcome them using feature subsetting, regularization such as L1, L2, and elastic net, and dimensionality reduction using PCA, factor analysis, and LDA based on what kind of problem you're facing. Perfect. I've gone a little over time, but I'm going to pass it on to Chinmayi.
Thank you, Sumana. Thanks for laying grounds for what we'll be building upon. I'll be sharing my screen now. And hi, everyone. I'm Chinmay. And for the next 1 hour, we'll be understanding some of the code to apply the concepts which we just learned and see how it actually performs on a real data set. If at any point of time you're not able to hear my voice or see my screen, do let me know. And yeah, so we'll get started right away. So the data set which we'll be working on today is basically a data set to predict house prices. So because we are predicting like a continuous integer variables. It's a classic regression problem. And so as you can see on my screen, there is a small snippet of code to how to mount your Google Drive. So this is important when you're working with Google Colab and you have your data file in your drive. But for our this current session, we have our file in a URL, so it wouldn't be required now, but just for reference. And so let's get started with exploring or understanding the data set a little better, so that we can perform or we can actually code a very simple linear regression model and then see how it works. So for this, our primary goal is to predict the house price per unit area. And we are given various important attributes which contribute to the pricing of houses, like the date or the age of the house, and so on and so forth. And so, so for this, we are using a linear regression model, and we will be using the scikit-learn inbuilt linear regression model. So what it does is it uh, it makes the building the model a lot easier, because it takes care of a lot of different aspects which we just learned, like gradient descent, loss function, and that kind of stuff pretty easily. And so we'll be going through loading the data, and then we'll explore the data a little to understand the different features. Then we'll see what is univariate analysis and why it's important. And then we'll see about correlation, which basically is one of the key aspects when it comes to understanding a model, like how the input and output features are related. And then we'll be doing a little bit of feature engineering, because for our current data set, it plays a important role. And then linear regression, and then we'll be seeing, sorry, my bad, this should be regularization. And so we'll be doing L1 regularization, L2 regularization, and then loss function. And then in the end, we'll be comparing the performance for all the three models which we built. So let's get started with basically just importing a few packages which you'll be needing throughout the session. And this is the link to the first data file which we have hosted on this URL. And so we'll do, you can do train test split as soon as you load data as well. But what a classic problem which we run into if we do the train test split at the beginning of the data set is whatever pre-processing or whatever feature selections we have done, it just needs to be done on both the data sets. So to avoid all that complexity, we'll be typically splitting the data after we are done with the pre-processing step. And then for data exploration, the main goal of data exploration is to like investigate the number of features, the data types, the meaning, and the statistical relations, like what is the deviation in the data set, or what is the min max value, and similarly. And so the first step which I like to do when as soon as I get a data set is just print the head of it, or the head function on it. So basically it just prints the first 5 rows. It gives you a very rough visualization on what data set you are dealing with. So as we can see, we have our latitude, longitude, and then a few of the values are floats, and few of the values are ints, and then our predict or the target variable which we are dealing with is something in this range, and this is the values we would be wanting our models to predict. And then we see that this first column, which we can see on the screen, which is number, it's basically just a ID, and it is unique for every row. So it wouldn't be helping us find any pattern in the data or in any way contribute to the target variable. So we'll just go ahead and drop this in the next step. And then we will be dealing with, or we'll be checking the data types. So why this step is important is because sometimes we have certain kind of data types like objects and etc., which needs to be converted into a certain data type before we can perform any kind of mathematical calculations on top of it. And even if we have anything which is a string data type, it needs to be encoded and that kind of stuff, because any machine learning model or most of the machine learning models will need like a numeric input to be able to perform any kind of prediction or pattern estimation on it. So, which is why we check the data type for all of our input features. And then our step is to describe the data set. So describe has a lot of insight we can gain by describe. So we can quickly have a look at how sparse the data is distributed, or if there is a lot of variance, and what's the min value, max value. If there is a lot of skew in the data, like let's say that most of my data points are in the 75th row, then we know that there is a lot of skew in our data. But for this data set, I do not see any such abnormality. The only thing which I see, or the only pattern I see which kind of feels like it needs to be addressed is there is for the house price of the target variable, the max price is 117, uh, and but all the other, or the average, let's say, is 37. So it means that there are a few data points which are way above the average and are might skew the data. So we will do a few other visualization and explore the data further to just check our understanding and see if this really works. So one of the key features for univariate analysis. So let me start with what's a univariate analysis. It's like we are just plotting the distribution for all the features, and we are just seeing how they are distributed, and if there is any outliers or anything which needs to be removed or pre-processed before we can move with model building. So this is a very key aspect of pre-processing. And for this, I have basically plotted all of my features. So we'll be starting with transaction date, and I have plotted a transaction date histogram. So as you can see, for transaction date, I do not see a lot of outliers or any discrepancy in the data as such. So next we go to house age. And as you can see, there is an uneven distribution of data across all classes, but it's not too irregular, or it's not something which might cause a complete skewing of data. Similarly with so this is another very important aspect of the data set which might contribute to the target variable. It's like the distance of the nearest station. So as you can probably intuitively guess, the closest the houses to the station, and more people will prefer it, and higher the prices would be. And so we see that a lot of houses are close to whatever the station distance is, and we do not see a lot of skew in this data. So we are just going to not address this for now, and then we move to number of stores, which is again a key factor, and the data looks good. Then we are dealing with latitude, longitude, and latitude, longitude. Whenever there is like a geo coordinate in the data set, it standalone wouldn't make much sense because it's just point information. And so we are going to deal with these couple of columns later on when we go to feature engineering, and then I'm going to explain which features needs to be primarily addressed through feature engineering, and what's the primary reason for performing feature engineering. So moving on, next we have the target variable, and as I felt in the initial describe step, there are a lot of data points which are beyond the 70. If you see the x-axis, beyond the 70 or approximately beyond the 70, but this might completely skew the data distribution because there are so few. So I just want to go ahead and see like how many actually data points are above 70. So if I first of all, I'll start with what my like lowest number is, and I want to see what's how many data points are above 100. And from what I can see, um, above 100 there is just one data set. So and then if I check, then above 70 there are 6 data points. And so what I would do is because there are just 6 data points out of the entire data set, which I think it's like 414 rows. So it does not make sense for such a huge, like it's how we know that the skew data is skewed is from 10 to let's say 70 we have all the data points, and from 70 to 120 we have just 6 to 7 data points. So these are clearly outliers, and we would like to handle it because there are a lot of issues which come with it, which we'll be discussing further. Um, so what I did is in these steps, I just chose any data point which is less than 70, and I removed or I eliminated anything which is greater than 70. So this is my length of new data frame, and I have simply dropped those rows which are outliers. So yeah, this is still where we do the pre-processing and actually see outliers and that kind of stuff. And then another key aspect when it comes to actually understanding or the two key statistical terms which help understand the relation between input variables and output variables, and also help in feature selection, are the correlation and the p-value. In this session, for the sake of simplicity, we'll stick to correlation, and p-value is again important statistical concept, which is a little difficult to grasp initially. So we will start this with correlation. And so if I have to explain correlation, it's basically like how closely the two data points are linearly related. So our end goal is basically to build a linear regression model which combines all of the input features and draws a linear line across a relationship between the target variable and all of the input features. So, but in correlation, we are doing the same, but we are taking one feature at a time. So here I started with finding the correlation between transaction date and sorry. So finding the transaction between finding the relation between the transaction date and the house prices. And if we see, it's most of the transaction dates are categorical, so this relation is not actually making much sense. Next, we move to the house age, and if we see this graph, when you plot a co-linearity or correlation, and if you find the output to be this kind of graph, basically means that there is very less correlation, or this feature, it's not particularly a good contributor or estimate of the end target variable. So this is a classic visualization for when there is no correlation, because it's like all the data points are scattered for every target variable. The data points are very scattered, so there does not make much relation or much it does not make much sense towards the target variable. Next, we will move to plotting the relation between the distance to the nearest station and the house prices. And like we discussed earlier, it's one of the key aspects when someone chooses a house to live in. So if you see this kind of plot, once you plot the input and the output, this is a classic example of a inverse correlation, or lesser the distance of the station, higher the price, higher the target variable, or higher the prices. So if you like, this is like a inverse line, and it's not really a line because we haven't scaled the data or a bunch of other pre-processing which we can do on the data set. But if you can still get a rough idea of how this is related, because there is a clearly visible inverse pattern or inverse line between the feature and the target variable. Next, moving on, again, this feature doesn't, it's like a completely categorical feature, and there is no immediate visibility in the pattern. So this is mostly about correlation and how it contributes to the Y or the target variable. So now coming to feature engineering. So like we discussed, feature engineering is important when we see that there are two features which can be combined into one feature, or if there are multiple features which individually do not contribute much towards the output variable, but when combined, they'll make more sense towards the output variable. So when it comes to latitude and longitude information, these are basically two sets of coordinates, and individually they do not make much sense, but we kind of want to find what's the exact point. And then we kind of somehow wants to put a value on it, which actually contributes towards the output variable. So for this, since we do not have any distance to take into account, what we have done is we have taken the distance from the absolute or the zero coordinate of the world. This formula basically deals with that. It's just a formula, and it's just a formula very specific to when you're dealing with geographic coordinates or data set which has geo coordinates. It's not much you can learn on. It's just something which you use when you have to find the distance. And so here I have basically ended up finding the distance, which I'll be using for going ahead as a feature. So I have added this to the data as a feature. And then in the next step, because I have already combined latitude and longitude to perform feature engineering and find the one feature which I want to keep, I'm going to go ahead and drop both these features. And then we are moving to linear regression. So if you remember from the slides, so basically our goal is to find the best fitting line that minimizes the residuals across all the data set. And so we also learned that the steps we take towards optimization is called the learning rate. And what happens in scikit-learn model, when we use scikit-learn linear regression model, it takes care of the stochastic gradient descent and learning rate like internally. And we do not have to externally specify or control it. We can fine tune it using different parameters and variables, basically parameters, but that we will discuss when we come to regularization part. So moving on, we basically just started with splitting the data to X and Y, or the input features and target variable. And then we have split the data to train test split. This is the random seed which we discussed for keeping the split frequent through all of your run. And again, we just check the data types to see if they all are same, and something hasn't changed while we are working with the pre-processing. The next step is we are simply going to use linear regression, and this one line of scikit takes care internally of the entire step of stochastic gradient descent and fitting the training data the uh, with the labels. And now in the end, we have this linear reg is our fitted model. And then, as we discussed, the primary formula for linear regression is we have to find a output variable y where which is equal to mx plus b, and b is the bias. So for this, if we have to see what's the bias and the intercept, so your bias is almost equivalent to your m in the mx plus b, and your intercept is the b part of the formula y is equal to mx plus b. So if you want to print what's the coefficient and what's the intercept which the model has computed internally. So this is the coefficient for all the different features which we have, and a high coefficient value means values or the output target is highly dependent on this particular input feature. And negative high value also means that it's dependent, but in a inverse way, which we saw for housage. And similarly, if we see for other features, it's like we any of these values means how much dependent the output variable is on the input feature. And moving on, the intercept is the basically just the b or the bias part of the model. And so this just basically takes the test data set which we have and makes a prediction based on it. And this is again used when we have to find how well the model performs, or the cost function and the loss function of the model moving ahead. Next, we also want to do regularization on the data set. And for that, we have this Lasso inbuilt library provided in Scikit. So it's again, you can import this via just using linear regression Lasso. And similarly, this is for L1, and linear regression, a linear model Ridge, which is for L2 regularization. So going back to where we have used it, the most of the training and prediction part will be same as linear regression, except for there is a term called alpha. And uh, this is basically just a normalization of the data, which once you set to true, it performs better as compared to if you do not set anything. So this alpha is one of the key terms which we came across in the slides. And so what this alpha decides is how much we want to penalize, or how much we want to make the coefficients closer to 0. So as Sumana explained, like basically the idea behind regularization is it's just going to make the fit as simple as possible. So our fit in the training data should be as linear and simple as possible for the prediction to avoid any kind of overfitting. And so, but if you over penalize, that's also not going to perform well. So you have to find a kind of sweet spot between different, and try different alpha options and see which one performs well for your data set. For sake of this data set, since it's fairly simple, and I wanted to show a very simple starting point. So I have kept the alpha 0.001, which is a very standard recommendation or standard starting point for L1 regularization. And I'm sorry, this is again regularization. And so I have kept the alpha as 0.001. And similarly, when we print the coefficients or the correlation between the features and the target, this is what we get. And the intercept is slightly different. There is a change in the kind of intercept we are getting. Then we have made the predictions and stored it in this value. And then we go to L2 regularization or ridge. And here I have kept alpha as 0. But you can keep the change this alpha to anything. Alpha is equal to 0 basically means that there is no regularization. But I just wanted to demonstrate this option, and going ahead we'll be making a comparison between different models. So I have kept the alpha as 0, but you can change this, and actually the best practice would be to try a bunch of different alphas for your L1 and L2 and see which performs best, and then go ahead and build your model with that alpha value. And then going ahead, we have printed the coefficient and the intercept. And so this is my final target value. And a key note or a key point which I wanted to mention here is one of the main differences between L1 and L2 is L1 is primarily it will perform your variable selection, or like we mentioned, if you have a lot of features in your data set and you want to reduce or you want to select the features which contribute most significantly towards your target value, then L1 helps with that without doing any or without you selecting the features. It helps you select the features for itself by setting the coefficient for some of the features which have very less coefficient relation or co-linearity with the target variable to 0. And on the other hand, L2 or rich will keep all the features. It will shrink all the coefficient of the features to close to 0, but it will not set any of the coefficients to actually 0. So it will not remove any features from the data set for you. And so going ahead, we want to find now that we have fitted our model and we have built our model, we want to see how well it actually performs, so that we have a way of estimating like if it actually works on the data set. So for this, we primarily have loss functions. As Sumana explained, loss function and cost function are very interchangeable. Loss function is primarily used for all the data points individually, and cost function is the cost function of the whole model. So it's like aggregate of all the loss functions across all the data points. So cost function is when you are talking about the entire model, and loss function is when you're individual data points you have calculated. And so here I have used three loss functions which we learned: mean absolute error, mean squared error, and RMSE, root mean squared error. And so first of all, this ypred is my predicted labels through the simple linear regression model without any kind of regularization. So if we see here, this is the simple prediction we have made using linear regression. We haven't used any kind of regularization in this. So I want to see how well it performed. And so these are the values here. If we have to like see a quick way of how well this actually performs. So root mean square error is a good indicator when it comes to, we want to quickly see like if our performance of our entire data set is somewhat close to the average of the data set or not, because a root mean square error actually scales and scales your output label and your error to the same scale as each of the individual errors or each of the individual data points. And so one quick way of understanding if the model is actually performing well is we quickly compare RMSE with the average which we found during the statistics. So let's quickly do that. So it's 9.07, and we'll go ahead and see the average value of this data set. So if we see our average is 37. So because our model is our error is way lesser than 37, so it's like we are our model is still like doing a pretty good decent job in prediction. And so moving on. So similarly, we calculate the different error values or different loss functions for the L1 predictions we made and the L2 predictions we made. And if we see for the RMSE values, all three of our models have actually performed very similarly when it comes to, sorry, so very similarly when it comes to the data set we are working on. And two key aspects of, or two key reasons of this I can think about is that first of all, we have less columns, and regularization is much more visible or has a much more significant contribution when you are working with a data set which has multiple columns, which leads to overfitting. And so we kind of want to reduce the contribution or the um, coefficients of some of the columns very close to zero. So in our case, since we already have very less columns, there isn't a very visible or significant difference in predictions. And the second reason I can think of is we have already worked on removing some of the outliers. There is still a lot of pre-processing which can be done, but we did a very basic outlier pre-processing. And so because outliers contribute towards variance and overfitting, so since there is already some outlier pre-processing done in this data set, there isn't a very significant contribution of regularization here. So after this, we'll go ahead and actually compare between the predicted values and the actual values for the first 25 of the data set. So if we see, most of the values are pretty close. There are a few values which are very far apart, and linear regression is one of the first or the basic regression models which we can use. And there is a lot of steps we can take to further improve our models. Like we discussed, we can try upon different aspects of or different values for the alpha, and we can do even more pre-processing. Pre-processing is something you can incrementally improve a lot of on your model performance if you spend a lot of time on pre-processing. And apart from that, we see we can also fit a more complex model to have a closer fit to the data. But for a linear regression, this is the kind of performance we are getting as of now. And next, we want to just plot this relation between the actual and the predicted for the same first 25. And this is the plot. And like we discussed, some of the data points have a very difference or a huge difference in the predicted and the actual values. Uh, so we definitely have a lot of scope to improve here. And then we plot the different kinds of regularized as well as non-regularized data values here. And like we saw in the error values, that there isn't a very huge difference between the regularized and the non-regularized values and or prediction capabilities. And so most of the data points are pretty close together. So you might not be able to visualize it in this plot, but it's like one data point is overlapping or one point is overlapping over another. So most of the predictions are close together and there isn't much difference in how the prediction works. So yeah, this is basically how we have done with the prediction. And so since we have some time left, what we will actually be doing is we'll be trying a few different alpha values and see how this actually works for our particular data set. And so I'll just go ahead and plug this 0.1 data set here, or 0.1 value for L2 regulation, and see if it makes a significant contribution towards the output values. And it definitely has to improve upon the RMSE, because we kind of have a baseline with the non-regularized version and we want to improve upon it. And if we see there is a slight improvement in the after we have L2 regularization and after we have um, set the alpha to 0.1, the ideal thing to do here would be to try out a bunch of different alpha values and then decide like which values actually contribute the most towards the output. And yeah, so that's something we can all particularly build upon and work on. And so for trying a few of these functions and for testing or trying whatever you have learned throughout the session on a slightly more complicated data set, we are going to have you work on a small data set, which is basically a kind of a homework data set for us. And so if you just give me 1 second. So if you refer to this data set, or if you refer to the recommendations we have for the homework data set. So this is our New York taxi fare prediction data set. And this is actually a slightly more complicated data set, but it's really good to build further on all of those concepts which we learned, like trying out different values for alpha, for regularization and that kind of stuff. And this is the kind of RMSE values, which is the like estimation of if you are performing well or not. And this has a huge data set. It's like actually, I guess it's close to 5K or these many columns. So it's a really huge data set. So you can see a very clear difference with regularization. Once you perform regularization on it, you can see a huge difference between a non-regularized and regularized version. And so we urge you to go ahead and try this data set. And this is most of the resources which we have, which will help you understand most of the concepts we explained today. There are a lot of videos which we have added links to in the slide, which are by Andrew Inch. And since regularization is a vast concept, and uh, you can learn much more, and the concepts will stick with you much better if you work through a few more data sets. We highly encourage you to go through these few of these videos and work on this data set. And I guess, yeah, I guess that's all I have for now. And if you guys have any questions, I'll be happy to answer. Or I think we are good to wrap this session for now.
Thank you everyone for joining. The chat has links to register for our upcoming sessions. We would be sharing the recording from this session and a blog post by our community member early next week. So keep your eyes out on Slack. If you're not yet on Slack, I definitely urge you to join Slack so that you have immediate help from the community. Plus, you can reach out to the leaders or panelists who are working on this session. And can access all of our previous recordings. All the notebook links are also available. There are recordings and blogs for all 3 weeks that have happened till now. And this week will be posted on Monday or Tuesday, actually. So early next week, keep your eyes out. Thank you so much for everyone for joining from all over the world. It's been great to walk you through this and answer all your questions. And we really look forward to seeing you all next week.